Alrighty, I think we will get started. Expect a few more folks might trickle in, but we're good to go now. Have some intro slides to begin with. For those of you who are returning after our first webinar, thank you so much for coming back. We missed you. Thanks for coming in right before the holidays. And those of you who are new to our Future Foods program for space, thanks for joining us. So we're here today to go through opportunities for future foods and space health research. And we're really excited to have our guest speaker lined up today. I'll introduce him in just a minute. So some quick overview of what we're expecting to cover today, which is a quick recap of this program, the Future Foods for Space program. Then going to have our guest speaker, Dr. Michael Wiederoder, and then we're going to go through some opportunities in space health. So by way of a quick recap, the Future Foods for Space program is a joint effort with UC Davis and Tufts and funded by TRISH, Translational Research Institute for Space Health, where our goal is really to bring all the great minds and folks who are involved in sort of future foods, whether it be faculty, postdocs, industry researchers, and so forth, to focus on space health with an emphasis on the astronaut food challenges, whether that's the food matrix itself, the health outcomes, or logistics associated with it. We have a few different programs that you can see lined up on our little summary graphic to the right. And today, this is hopefully self-evident that this is the webinar program. So within that, I should say we have 3 main webinars that are planned. So our first one was an introduction, so really helping to initially orient folks to the context of future foods for space. And you'll see throughout the presentation that there are these blue boxes that say, click here to watch or to access. When we're done with the content today, in the talk, we'll send out a PDF copy of the slides for folks to be able to follow up on some of these links if they're interested. So you can take a look at the recorded webinar one there. And today is the opportunity. So it's our second. We're continuing to progress. We really appreciate already your feedback from the first webinar. So beyond the topics that we're going to cover, I also want to sort of hone in on what we're expecting to sort of bring from a value or sort of key takeaway perspective. So the first is understanding that opportunities in space health are not just within space health itself. So thinking about how research into the food systems for space also build translatable skill sets into different areas. So today we're really lucky to have a speaker who's going to give a great overview of food for defense and military applications. And then we're going to tie together sort of how you connect between space and defense here. And then second, we also really want to provide you with different resources on how to engage with existing space health opportunities and resources. So without further ado, I'd like to introduce our speaker today, Dr. Michael Wiederoder. Mike is the Strategic Integrator for the Combat Feeding Division at the U.S. Army DEVCOM Soldier Center. He oversees the science and technology strategy for the program and engages external stakeholders to support transition of field feeding capabilities to the warfighter. And I hope he forgives me just reading verbatim his bio off the slide. So with that, I will stop sharing my screen and let Mike take it over from here. Thanks, Mike.
Yeah, thanks for introduction, Matt, and nice to meet everyone virtually. You should be seeing my screen, is that correct?
Yep, we can see your screen now.
All right, so as Matt said, I work in the U.S. Army Combat Capability Development Command Soldier Center, or DEVCOM. We're here in Natick, Massachusetts, so actually about 30 minutes to an hour away from Tufts, depending on the time of day. And our program here develops food for the military, specifically what we term as field feeding. So feeding not in cafeterias or at installations, but really expeditionary. So you'll see during this talk, I think there's a lot of analogous work that can be relevant for space applications as well. So a little bit about myself. I grew up in Michigan. I went to Michigan State University. So my undergrad was biosystems and agricultural engineering, and had a lot of interest in food engineering. And so that's kind of how I got into that space. Then went to the University of Maryland, College Park, where I did a master's in food science and then a PhD in bioengineering. I was fortunate enough to actually do a 6-month postdoc in South Africa. And then I ended up starting here in Natick as a postdoc. So I was a contractor researcher on a fellowship for a couple of years. And then I've been a civilian government employee for about 6 years. So I'm not an enlisted member of the union military. I don't wear a uniform. I'm just a government employee, subject matter expert. Was a researcher for about 6 years, and now I work in our program office side for the past 2 years now. And then, of course, the nice disclaimer that these are my opinions. They're not necessarily representative of the U.S. government itself. So with that, what is the DEVCOM Soldier Center? So our research lab here in Natick. Overall, there are 1,000 employees. As I mentioned, 50 are military, so 50 are uniformed members of the military. And about 700 of us are civilian employees, just government employees, and about 260 are contractor employees. The majority are here in Natick, but we also have a group in Orlando, Florida, that does work. And then we also have a group in at University of Southern California as well. And I'll talk a little bit about some of their mission areas later. So what does the Soldier Center do from research and development? Work on clothing and protection and equipment. So anything that an Army soldier wears that has to carry, that is not the gun, is designed here. So boots, uniforms, helmets, backpacks, hydration systems, ballistic vests, all sorts of things the science is done here. So we have a lot of material science expertise in that area. Human systems and integration. So we have people that do cognitive science performance. We have people that are more on the biomechanics side. And then we have people that do training and simulation. And that's really where those groups in Orlando and USC come from. So in Orlando, they're developing kind of virtual reality simulations for different applications. The recent one was training people to do eye surgery. So you essentially could use virtual reality to learn to do eye surgery. And then, of course, at USC, you have all the world's best animators who could work for Hollywood, but a lot of that research and technology we develop could also be relevant for the military. We have an aerial delivery group, so everything that drops out of a plane, anything from parachutes to gliders. We have expeditionary maneuver support, so these are things like temporary shelters, shipping container type systems, tents. If you need to make a city halfway around the world, you need those types of capabilities. And then finally, combat feeding, which is what I had mentioned. So we are a joint service program. We sit in an Army installation. The Army runs the program, but our customers are the Army, the Marine Corps, the Navy, Air Force, and the Defense Logistics Agency. And technically, Space Force falls under us, although right now Space Force is a terrestrial organization that eats primarily in cafeterias. So we don't have any unique feeding products for them yet, but if they do end up having a deep space mission, we would take that on. And we actually do have a lot of collaborations with NASA, both on technologies, but also actually even some of the food that makes it to the space station was made here in our pilot plant. It's then irradiated and packaged so it's safe, all the organisms are killed, and it goes up to space. So we actually have a lot of interesting collaborations with NASA here in our group. So some of the historical innovations, so some of the scientists and researchers here have developed the technologies of dehydrated milk and eggs, converted rice, high pressure processed foods, which you've ever seen guacamole in the store, that's high pressure processing. And while we didn't invent the Hot Pocket, we came up with a lot of technologies to allow what we term a shelf-stable sandwich. And really what that is that the water activity of that bread on the outside is the same water activity as the filling on the inside. So you don't end up with either a dried out filling or a soggy bread. I actually found out this week that scientists also are responsible for the McRib or restructured meats. So a lot of the work here that was originally meant for the military, it was kind of ended up on our grocery shelves and in our restaurants. So when we're developing field feeding solutions, both the food and the equipment, right, we have a lot of constraints as we move really into those kind of expeditionary operating environments. So one is that whatever material we develop has to work in every climate, whether that's the Arctic, whether that's the desert, whether that's the tropics. Logistics is a huge constraint. We're constantly focusing on how do we minimize the burden of moving food from point A to point B whether that's at the individual level, an individual who has to carry their food and water in their backpack, vehicles that are used to transport food and water, ships, air, etc. So anything we can do to reduce that logistics burden. And I would imagine with space, right, you multiply that times 100x, right, because the cost of rocket fuel is so high. Every ounce matters on a spaceship, whereas maybe in the military, every pound matters, every ton matters, things like that. We have a unique shelf life requirement. Our food has to be shelf stable for 1.5 to 3 years. And that's so that these rations can be pre-positioned around the world for the military. And it's part of why we exist, because there's not really that need for that shelf life in like the civilian commercial market. Waste disposal is a huge problem. Right now, one of the ways we get that shelf life is we use a lot of packaging, but then we have to get rid of that packaging abroad. Right, the city dump truck doesn't come pick up our packaging. And so what that means typically is that we end up having to burn our packaging around the world or pay a lot of money to figure out what to do with it. Our nutrition needs vary for our warfighters. So you can imagine someone in the Arctic who skis for 15 miles a day or marches 50 miles per day. It's just very different nutrition needs than someone who's maybe operating in the desert and kind of driving a vehicle. But they all get the same food, primarily. So we're constantly balancing offering enough food products to meet those diverse mission types, while also making them not too many different unique items so that it's easy to procure them from industry. And finally, the taste and convenience are important. I would say our number one technical problem is that if the food doesn't taste good or if people get bored with the food, they don't eat it. If they don't eat it, they run into energy deficit. And eventually it will affect their performance. It will affect their ability to do what they need to do as warfighters. So, right, we have all these technical constraints, but at the end of the day, food is about making people happy. It's about morale, and it's about kind of delivering an experience to people. And I've heard similar anecdotes from astronauts talking about kind of the food that they need in space, really, for that morale as well. A lot of the unique workarounds they figured for that. So when it comes to rations, I'll try not to spend too much time on this, but we have individual rations, like the meal ready to eat, or MRE, an assault ration. So this is a ration that's for an individual, but it's meant specifically for people like who need to do short missions, that's maybe a week or something like that. Whereas the MRE is intended more for eating 21 days in a row, as an example. We have a meal cold weather. So this is an individual ration, but it's freeze dried. So that way a freeze thaw cycle doesn't ruin the packaging if it's in an Arctic environment. And so there's the freeze dried items that you add hot water to make a meal. It's very similar to technology you would see at any outdoor store if you're buying some of those freeze dried items from an outdoor store. We also have group rations as well. So lots of different types of rations. Some require refrigeration, some do not. We have one called the Express, which is kitchen in a box. So it's actually just a box. You pull the handles and it heats up and you get a hot meal in 30 minutes. And then we have some of those supplements or enhancements I mentioned. So these are things like additional food items, for example, for high altitude and cold weather or hot weather, as a way to help with performance in those specific environments. And so altogether, these rations are produced largely. I think there are 2.5 million cases of MREs purchased every year, or 25 million individual MREs. So the scale is quite large. So even small differences and changes make a big impact across the entire supply chain. Next, I'll talk about some examples of projects we've done in the past and the types of work we do here based on kind of the needs of our customers. So this product I'll talk about first is an example of a nutritional intervention, and it's called the Performance Readiness Bar. So our partners who work on medical nutrition and human performance, we're getting a lot of data from basic training that stress fractures and musculoskeletal injuries in general were a problem. And that makes sense, right? Because you have 18-year-olds who have been at home, probably at varying levels of physical activity, who are inserted into an environment where they have to do a lot of physical activity for 12 to 16 weeks in a row every day in basic training. And so what we developed with our medical nutrition partners is a calcium and vitamin D fortified bar called the Performance Readiness Bar. And it took about 5 to 10 years, but the first step was they identified we would like a bar that has calcium and vitamin D based on scientific literature. Then our food scientists here developed some prototypes. Those prototypes were then tested with users. So all the food we develop at some point is tested by warfighters in a relevant environment. A lot of times it's a training exercise. And finally, after all that work, we were able to develop the technical specs for a product that could be made and produced by industry. And right now there are, I think, 3 flavors: chocolate, salted caramel, and berry cherry berry, I believe is the name of it. And so we're working on more flavors because right now this is called the night bar. So if you're in basic training, you eat this every night before you go to bed. So again, we're trying to think of ways to overcome some of that menu fatigue. And while we don't have a negative control and a positive control to prove that this works, it's clear that this, along with other things, has really reduced the amount of these musculoskeletal injuries we're seeing. And as a result, more warfighters are leaving basic training and entering the force. Tube foods. So this is a unique project we have. The Air Force has these pilots who fly in U-2 spy planes, and they're in the air for up to 12 hours at a time. And so they were having problems getting nutrients to kind of keep going. And so they worked with our group here to develop what we call tube foods. And so there are these foods that we make in-house because we don't buy so many of them that it makes sense to buy them from industry. But you can see there are flavors like apple pie. There's caffeinated chocolate pudding. So there's some caffeinated items as well. There's a truffle mac and cheese. And it's not like a complete puree. There's a little bit of chunks in there to kind of make it a more pleasurable eating experience. But it's still small enough to go through that tube. And so up to 15 recipes now, including a spaghetti and meatballs, which was based on the inventor's mom's recipe for spaghetti and meatballs. It's a program that's still ongoing here for us. Another project I wanted to talk about is the meal ready to eat pizza. So as I said, that meal ready to eat needs a 3-year shelf life, and we would do surveys, and as a result, within the MRE, there's like an entree item, there's some sides. And so that entree is retort processed or canned for that shelf life. So things that would normally taste good out of a can, like beef stew, chicken soup, chili con carne, those items go really well. But we would give out surveys and people kept saying, oh, we would want pizza and macaroni and cheese. And so our scientists here have tried to figure out how could we get pizza with a 3-year shelf life. And so through a lot of trial and error, they're essentially able to balance that pH, the water activity, and develop a packaging and try a lot of different recipes to kind of get to a solution that had that. And then ultimately work with industry to scale it up, and then also do a test and evaluation to make sure it actually was acceptable. So now one of our 24 MRE menus includes pizza as the main entree. So I mentioned packaging is a big deal. I would imagine it's an even bigger deal in space, but it's a big deal for us too. As you can see in that top left there, this is how many components are in that meal ready to eat. So it's a lot of trash to throw away, right? To get rid of. And so some of the things we're looking at are new materials to provide oxygen and water vapor barrier to enable that shelf life, but get rid of the foil layer in there right now, because that's one of the main impediments to maybe recycling, repurposing. We're always looking at ways to reduce the total packaging. And so the machine shown there is called a horizontal form-filled seal. And really it's just a piece of equipment that allows us to reduce the total amount of packaging. And even though it's kind of a small change of that one item, across the entire supply chain, we reduce the amount of plastic needed by 1 million pounds per year. And then looking towards the future, we're looking at ideas like compostable packaging, degradable packaging, or even using packaging as feedstock as an input for conversion into something else. So maybe waste to energy conversion, waste to food conversion, even things like that. So I mentioned we do a lot of field feeding equipment. So this is equipment that prepares that rations, and you can see the size and scale, anywhere from small heaters that can heat a couple trays, to trailer-sized kitchens for the Marines, to even ships, so things like submarines, where space is definitely at a premium, but not energy, but space is at a premium. And so thinking of ways to develop kitchens and also the rations for those kitchens to feed the warfighter. And finally, we have a group that works on food safety as well. So looking at technologies to detect and mitigate contaminants and adulterants in food and water and on food contact surfaces. And so there's things like rapid biosensors. So here you can see a sensor that changes colors in response to the presence of salmonella, as you call it, salmonella on this one. Looking at some novel decontamination solutions, so ways to sanitize that don't require a lot of water and bleach, which are at a premium in that kind of expeditionary operational environment. And then also looking at multispectral imaging of surfaces. So can you take pictures of things to assess their safety and potentially their quality? And this device right here is actually a near commercial product that we're doing testing evaluation on. We're also collaborating with NASA. There's potentials to use this type of technology in space, either for safety applications or even to monitor plant health if we're trying to grow plants in space. So I saw a question from Crystal. Apologies for that. What's the source of the vitamins for the bars? So the vitamins are just fortified vitamins. They're vitamins that we would buy from commercial food suppliers. So similar to the way that you would get vitamins from the grocery store, you can use those same vitamins and just fortify them into foods. So that's the solution there for that. So one other area that we're starting to get involved in is biomanufacturing of foods. And really what it is it's part of kind of bio-industrial, almost a revolution, right? There's a lot of new and alternative kind of materials being produced in kind of fermenters or other types of biomanufacturing processes that typically we would resource from either non-renewable resources or chemical synthesis. And so we think there's a lot of opportunities of taking products that are being developed by industry, primarily for that civilian market, but repurposing them for military rations. And this could be replacement of foreign ingredients to increase supply chain resilience, ways to counter bioterrorism of our agricultural supply chain, economic security, lowering costs of the rations, potentially enhancing the flavor, texture, or taste of the rations by using some of these new materials or ingredients, food ingredients, right? Potentially enhancing human performance, and also potentially helping with special use cases. So whether these are allergen-free foods, we also have people, we have vegetarians, right? So we have rations that are vegan or vegetarian. We also have rations that are kosher and halal as well for those populations. That kosher halal may not be relevant to biomanufacturing, but those are some of the other considerations as well when we're developing these foods, is that there are going to be certain dietary restrictions and kind of requirements for different types of populations. And so as we think forward with the generations, really one of our primary goals is that demand reduction. How do we reduce the size and weight of the operational rations to reduce that individual soldier load, and then also logistics of shipping through technology. So some of the things we've looked at are advanced concentration through membranes of materials, using a technique called vacuum microwave drying to dry out foods while enhancing their quality over products that you would dry using heat only. Sonic agglomeration, so using sound waves to densify food. We've used some of those technologies to develop what we call the close combat assault ration, which is a very military name. But really what it is that close combat assault ration is 2,800 calories in a bag, whereas the MRE, 3 bags equals 3,600 calories. And so what really enables is that it's kind of a 17% weight and a 39% volume reduction compared to a prior ration called the first strike ration, and it's 74% smaller than that MRE. So it really does, especially at that individual level, kind of allow people to endure longer in a military environment. And so we're working on that, but there is a limiting factor. You know, calories and nutrients have inherent mass. I think estimated that you need probably about 1.2 pounds of just biomass per day to get enough grams of protein, carbs, fiber, and fats to meet our nutrition requirements. And the military nutrition requirements are very similar to what you would see probably on your FDA kind of nutrition facts that you would see on products you would buy at the grocery store. So our rations have to deliver that certain level of macro and micronutrients. But trying to get below that 1.2 pounds a day is essentially defying physics. We're trying to think of other ways to produce water and food in kind of the indigenous environment instead of having to ship them through the supply chain. And so we call this concept untethered logistics. I've also heard the words assured provisioning. And really what it is, it's being able to take advantage of the indigenous environment to produce water and food. So we're looking at technologies like atmospheric water harvesting. What if you could put a dehumidifier in a soldier's backpack or a warfighter's backpack? So that they essentially could produce water on the move, as long as the energy required to produce that water is not too burdensome. And we've looked at other technologies like desalination or kind of water treatment solutions in the field. And then one that's a little bit even more in the future is this idea of point of need nutrition. And so this idea that you could develop essentially a bioreactor and associated kind of equipment to create a system that can produce food from feedstocks like air, water, and electricity. And I'll talk a little bit about that concept more on this next slide. So what do when I say point of need production, what are we talking about? So, you know, to make food, you need nitrogen, oxygen, carbon, and hydrogen. And how you source those is kind of dependent. And so, you know, some of the demonstrations we've seen are that people use things like air, and then do a combination of both thermochemical processes, and then also kind of bioreaction. You can take the nitrogen, oxygen, and carbon from the air, and then you get hydrogen and water from the oxygen from electrolysis of water. And with those combined, along with some kind of minimal nutrients and seed microbes, you can ferment foods kind of anywhere in the world. So as long as you have enough energy, clean water, and equipment, you can pretty much produce food wherever you'd want to. And so some of the concepts we've seen are people are growing mycelium, so kind of fungus, essentially, yeast cells, mycelium, as a way to create some alternate protein sources. We've seen fermentation, so you get edible fermented products, a lot of yeast, bacteria, things like that. And also we've seen a lot of concepts looking at algae as well. And that light source could either be a powered light or even the sunlight. And so these are some of the concepts that we're looking for. And I'll just give examples of a couple projects that are using those right now. So DARPA has a project called Resource. And essentially what they're looking at is taking mixed waste, so paper, plastic, cardboard, potentially food waste, and putting it into a system that breaks down those products chemically and then builds them back up using precision fermentation. And so the idea is starting with essentially trash. You can end up with petroleums, oils, and lubricants, or even a macronutrient like protein. And another program is this idea of cornucopia, is what's called at DARPA. And this truly is taking air and water and electricity plus microbes and turning it into a food, potentially even like a pudding or a shake. And so the idea is that you can avoid weaponization of food by producing this food anywhere around the world as long as you have adequate resources. And some of the potential products could be things like a jerky, a shake, a pudding, things like that. And so the end goal, right, of this concept is that we would want to provide a system that delivers on-demand nutrition at point of need in austere environments, reducing that soldier load and logistics burden. That technology is scalable and adaptable up and down. So it could be kind of in a shipping container like this on the back of a trailer. It could be a large shipping container, potentially for a humanitarian or disaster relief application. It could be on a ship, on a sub, And while it's not our mission space, you can imagine this type of technology being used on a spaceship, especially if we're talking long endurance missions to Mars, to the moon and Mars. And so there's it's a really interesting space. It's definitely current state is this type of work is done in research labs, and it's just a long bench with a series of different equipment that a student kind of moves stuff from point A to point B. But longer term, we're hoping you see that this is kind of an integrated system that is deployable and rugged and can be used for different types of use cases. And so with that, I'll end with kind of one last slide that's more, when I think of space feeding versus military feeding, how are they similar and how are they a little bit different? And so, right, for both cases, logistics are constrained. Your ability to move food around and water around is going to be constrained by the environment you're in. That demand reduction aspect is key. Every gallon of water, every pound of food, the energy you need to move stuff around, prepare it, cook it, and then just the physical size and weight, the footprint of all that stuff is really relevant. And any way you can reduce that total demand is extremely helpful. For space, right, the goal is to endure in space and have happy astronauts go as far as possible. And for the military, it's essentially for people to be able to execute their mission for as long as possible, despite maybe what their enemies may be trying to do. There's definitely a major difference in the acceptable costs. I would imagine like the amount of money you can spend to feed an astronaut is per person is significantly higher than what you would spend on a soldier. And so I think this is interesting because I think that a lot of the technology developed for space feeding might cost a lot of money, but then it can inform military adoption if there's a way to make it kind of lower cost and easier. Personalizing nutrition is always an interesting aspect. How do we monitor human performance and then provide nutrition to help sustain or enhance that performance? And I think, right, there's a lot of interesting ideas around wearables, or at least understanding different nutrition requirements in different spaces. But then there's also that logistic constraint of it's hard to personalize nutrition in a constrained environment where your logistics are constrained. Morale is important. I heard somebody say when the soldiers stop complaining about the food, that's when you need to worry. Because if they're not even complaining about the food, it means that they just don't care anymore. And similarly, I've heard a lot of people kind of say, I had a bad day, but then I had that MRE and it had a heater in it and I had a hot meal and it just kind of made that day not so bad. So we always have to keep morale at the top of mind as we're developing new technologies. And finally, I think there's a lot of opportunities to leverage biotechnology in this space. There's a lot of capabilities that you can get by using biotechnology to help with these feeding, field feeding or space feeding, if the public and politics allow. So I think we've had some pushback here on I guess cultured meat. So we've had people in kind of cowboy hats go on Fox News and talk about how we're feeding cultured meat to our soldiers, which is not true. But there's just enough kind of stuff out there that they could start that story. And I think as a result of the messaging, essentially, there's a lot of interesting politics out there. I'll leave it at that as a government employee. But I think it's important too that, right, as scientists and engineers, we have to engage with public affairs and people who kind of message to the public and understand that there are public ramifications of these technologies, in addition to just trying to make them work in the first place. So with that, this is our kind of our takeaway message is that we always try to empower, unburden, and protect our warfighters to outperform and outlast any adversary, anywhere, anytime. So thank you so much for your attention. I think we have about 10 minutes for questions, and I'll put up that conclusion slide just as a way of saying that, if you want to keep the conversation going, feel free to email me. I'm always interested to hear other people's ideas. If they're interested in learning more about the program or just to connect in general. So thanks so much for your time and looking forward to some questions.
Fantastic. Thank you so much, Mike. Really, really awesome presentation. So I can see In our Q&A section, we have a few questions. If we have time, I might even have some bonus questions for you from myself. But we can sort of start from the top. So I think we had one question about energy sources. So if you're on a ship with a nuclear reactor, energy is not a problem. However, what about in the field? What do we need to? What would systems need to consider for point of need production if they're in the field without that kind of energy source availability?
Yeah, so that's a great question, and that's something we talk about a lot. Because in order to power these types of systems, you need water and energy is a finite resource. So on a ship, right, that's, I'm me editorializing, but my guess is that if this becomes a reality for the military, ships are probably one of the first places you would see that technology as a way to just kind of let ships do their thing for longer without needing to be resupplied, which is something that we get a lot from our customers. And then if you think about the Army, right, there's some places the Army is where there's an existing grid they could plug into. And there's some armies where power is diesel fuel. You have to turn diesel fuel into electricity using a generator. And so in that case, you really have to do a trade-off of kind of, can you afford to burn the fuel to make the food? And so that's why I think, right, field feeding in the future is always going to be a hybrid between those rations. So moving a box of food from point A to point B, but also point of B production. And any improvements in technology that reduce the amount of energy needed to make a calorie is going to make it more likely that kind of the Army could use these in land-based systems. So that's a really good question, and it's something we think about all the time. And I would imagine in space, right, energy balance is key. Electricity isn't free in space either, so that's always kind of a key aspect.
Fantastic, thank you. To move on to the next question then, we have a question, what if the air is polluted? And I think if I were to sort of abstract that, it's about what do you do about the variability in the indigenous resources that you might be looking to leverage with, I think, a particular interest here on the atmospheric water harvesting?
Yeah, so that's a really good question. I think it's basically, you need to have quality control in these systems. And the cheaper and less humans you need to do that quality control, the better. I didn't talk too much about this, right? But labor is also constrained. And again, that's similar to space. Astronauts can only do so many things. So automation and not taking up labor is going to be important as well. So I think you need to make sure that you have to test and evaluate your systems in all sorts of environments, including pollution. And then you need to build in controls or tests so that people can validate that their food and water is safe if they're generated by these types of systems.
Yeah, those are really good points. So our next question that we have is about challenges with mammalian cells and cultivating them, potentially for a sort of a point of need system. I think essentially the question boils down to, are prokaryotics the preferred organism set that the military is thinking about for sort of maybe near-term biomanufactured food applications?
Yeah, I think based on the maturity of the technologies, our primary focus is yeast, bacteria, and algae. And then, right, mammalian cell or even plant cells, I've seen some concepts where plant cells are being incubated in bioreactors. Those are probably longer term, just because there needs to be more maturity in the technologies for those kind of more mobile, portable type applications, which I think is independent from maybe the industry application.
Awesome. So our next question, I'm just going to keep firing off. You're doing a great job. This is a 2-for-1. This is a BOGO deal. The first part of this question is about, you mentioned that the performance bar took 5 to 10 years to develop. Can you talk about the process, steps involved, and important considerations involved? That's the first question here.
Okay. Yeah, it probably could have been accelerated if we had more money, right? That's always a thing. And it could be accelerated if we didn't have to do shelf life testing. So part of it, right, is that we do accelerated and long term. So we'll do 6 months, I think, at 120 Fahrenheit And then we'll do chemical and microbiological analysis and taste testing, sensory analysis. Sorry, I'm using the real term. And then we'll also look at putting products in 3 years at 80 degrees Fahrenheit. Those are kind of the two tests that we do to decide if shelf life is appropriate. So I realize I'm going out of order. So the question is, what are the steps? So step number one is we have to identify a food that we think will support or enhance performance. And that usually involves scientific literature and working with medical nutrition experts and making sure that the literature we're looking at is a warfighter population, not a geriatric population, as an example. Then we have to do human trials. And there are kind of two aspects of human trials. One is you actually have to recruit the humans and do the work and analyze the data, which can take some time. And then two, an interesting food science problem is we need a negative control and a positive control. So you have to make a bar that looks and tastes without the ingredient, that looks and tastes and smells the same as the bar with the ingredient, which for vitamin A and D is not that big a problem, but we've had a bar where we want to add 50 grams of tart cherry extract to a 500 gram bar. And so figuring out how do you make that negative control is an interesting problem. And then finally, we have to, including that timeline is we have to get industry to make it. So we have to be able to write technical specifications so that industry produces the product we want. We have to validate industry's producing the product we want. And then the Defense Logistics Agency has to put them on contracts. There has to be open bidding, so no one's getting preferences and going around laws. So I think that's it. There's a lot of aspects of the process. One is it has to work from a material perspective. It has to work in the humans. And then the government has to be able to buy it from industry in a way that's fair and doesn't violate any laws. And then it has to actually get to the hands of users, and they have to know how to use it. They have to be trained on how to use it and when to use it and when to eat it, kind of thing. And I see a question about duckweed. I would love to learn more. As far as I know, we're not looking into duckweed, but I have heard of that in the kind of alt protein biomanufacturing type space. So that would be an interesting thing to explore more.
So Mike, we have 1 minute of your time left, and I'm hoping that maybe over some eggnog or what you will later the holiday season, we can have a chance to get some of these questions to you, and you can answer them leisurely if you have time, so we can get folks offline some responses because we're not going to be able to get to all of these. But I did want to know very quickly if there are any resources that you'd recommend for how folks to, whether they're already involved in the space community or they're more of a future foods community, how do they get involved in this space and this great work that you all are doing? I'm assuming your email is a great place to start for one.
Yep. Yeah. So you can always email and talk. We go to conferences. We go to like IFT. We go to future foods conferences. Then there's just like kind of a lot of programs. So it's just meeting, greeting, learning about people. And I do see a question about Sunita Williams. So I will take that one. So I had mentioned one of my colleagues came in and was like, I was going to stay home on Monday, but because of Boeing, I now have to make food for the space station. So yeah, we sent up an extra shipment for the astronauts that got stranded. But yeah, in terms of getting involved in the space, yeah, email me. We go to conferences. Try to be part of the greater community, and it's kind of people in the space are out there. So just like anything, it's about kind of getting yourself out there, getting your work out there, and making connections.
Awesome. Well, thank you so much again, Mike. It's been a pleasure having you on. Clearly a lot of excitement in the Q&A section as well. So, thank you so much. And with this, we will transition to sort of the next segment of our webinar now. So,
all right, thank you so much, everyone attending. Thank you, Matt and Olivia, for setting this up. A lot of fun, and we'll connect again later.
Cheers. All righty. With that, let me share my screen. So Mike already did a great job in helping us to understand how to go from defense to space. So I'll very quickly blow through a couple of slides here, which is to say, I think the image speaks 1,000 words here. where you can see the similarities in a lot of the, if you look at the military MREs and the prepackaged astronaut foods, there's a ton of similarities as was reviewed. And the design constraints for space technology, which we've gone over in the past webinar in more detail, actually have quite a few overlaps with military application considerations and quite a few with really what Future Foods specializes in. So with that in mind, I also wanted to just highlight one study that came out from the Combat Feeding Division when they did a collaboration with NASA on vitamin stabilization for low moisture products. So they looked at they were able to successfully, formulate foods to stabilize vitamins A, B1, B9, C, and E for 3 years. And really, when we think about this study, which you'll be able to look into in more detail with the PDF copy of this webinar, this is a good example of vitamin stabilization really being at the intersection of future foods, space exploration, and military. So with that, we're going to try something new. Before we move into the space health resources sort of dedicated section, we want to do a quick pulse survey. So we want to just ask a couple quick questions. You should see that this poll on Zoom just popped up. If you can help us to just respond to a couple of the questions in this poll, this will be fantastic for helping us to improve and evaluate our content. So I'll put on, 1 or 2 minutes or so. We'll sort of see as the surveys come in, and then we'll continue from there. Thank you for your time with this. Okay, that was awesome. Really appreciate folks getting the responses in. We'll keep the poll open just for a minute in case anybody needs a little bit more time to think about how they're doing on this. But for the sake of time, we've only got about 10 minutes left. So I want to make sure to at least give you an overview on some of these opportunities. So when we think about space health opportunities that we want to provide to you all that we think would be effective, we're trying to help engage people coming from very different places here. And so we have broke down opportunities by learn, engage, and apply. So learn really is literature, guidance documents, and organizations. Engage is what events and conferences might be out there that you might want to participate in. And then apply is sort of getting into a little bit of funding channels here. So as far as learn goes, I'm just going to highlight some of these resources quickly with the idea that hopefully we can add a little bit of excitement and help you understand if this is an important resource for you to key into yourself directly. The first is the decadal survey from NASA. So they have a series of these for their different domains. Here we're showing the biological and physical sciences research decadal survey came out in 2023. And it lists sort of the guiding priorities for the next 10 years for this entire program. So that's really important for helping you to orient. So there's only a few guidance doc here, so don't worry. Another guidance document that we think is really important for folks to understand that's out there as a resource, especially if you're new to this space, is the Human Research Roadmap. So this is NASA's Human Research Program, HRP, that provides public access to this roadmap. This roadmap is really, I would recommend one of the first places that you go if you have an idea for a research concept and you want to get oriented on, is that a priority for NASA right now? What's been done on it? What are some of the gaps potentially? And so I'm going to walk through one example for you to see sort of, so you can understand how it's structured. So if we look within the highest level of the risk hierarchy, the human health countermeasures, one of the risks that's listed within that is risk of performance decrement and crew illness due to inadequate food and nutrition. This risk sort of data page has quite a bit of useful information on it. So there's a short overview so you can see, an evidence report associated with this. You can see point of contacts. Is this active or is this sort of a closed risk, and so forth. You also get this really great risk rating permission type. So you can see how this risk is rated for different missions. So in this case, if you just look at the color coding, you can see that red is indicating sort of a higher risk that requires mitigation. So as you're progressing to missions that are more complex and longer in duration, this food and nutrition risk gets higher and higher. And lastly, it's not only about the risk here, but it also ties in associated documentation with gaps that are associated with the risk, other risks that are related, and mitigation strategies that they have developed. So please, this is a very important resource. Want to make sure it's on everyone's radar. And lastly, another really fantastic resource that came out only very recently. Big shout out to Engineering Biology Research Consortium here. They came out with their Engineering Biology for Space Health roadmap. This has 3 major themes for breakthroughs and milestones for space health. Food and nutrition is one of those 3. Would highly recommend folks taking a look at this for inspiration about what some research priorities might look like for you. Just to show you an example of how the report is structured here, you have a larger goal, such as increased palatability and stability of food, and different breakthrough capabilities associated with those goals, and then milestones that are listed by short, medium, and long term. So moving beyond the guidance documents, we have a series of sort of what we think are key literature to this space that could be important for folks. We're not going to share any of them right now, but they will be in the PDF deck. We took some time to really think about the different slices and dimensions of space health research that could be important. So here, each document that we're going to include in this, in the PDF copy of the webinar, will include different icons to indicate whether it's, which research topic it's related to, which food type, so is it prepackaged or bioregenerated, and then which proving ground. So was this sort of R&D early stage in a lab? Was this, all the way up in ISS? Similarly, we're going to provide some what we think are, exciting organizations that are involved in space health as well. You can look for this in the PDF copy of the deck. Again, we're trying to help you orient here by tagging it as either an R&D primarily organization, ground simulation flown, or is it up in the International Space Station? And so this is roughly organized by the technology readiness level of the organization that we think it typically occupies. So, but moving now from learning to engaging, we wanted to provide a list of a few different, exciting meetings. And I just want to take a second to talk on a really nice one that's upcoming, which is NASA's HRP Investigators Workshop. This is open to those that are currently investigators, but also folks who are not currently investigators. It's single-handedly one of the most useful times to engage with the community, learn. In fact, NASA has really structured it to be very interactive and learning to help folks understand NASA's priorities and sort of what's been out there. So it's a really, really productive environment for learning there. Of course, other community events, we have to plug what we've got going on. Stay tuned for other program elements that we're putting out. And similarly, Trish, who's funding our project, also has a great list of different webinars that they've done before, and they also have this monthly Orbit Rendezvous, where it's sort of a monthly seminar series that you can tune into. We find that this is a really exciting way to see sort of a pulse of the space health community. In the sake of time, I'm just going to skip past some slides here. Again, most of this is meant to be as a reference for you all. The Deep Space Food Challenge is interesting. It recently closed, but it engaged over 300 teams over 3 years for novel food production technology. So I'd highly recommend folks understand how people pitch their different angles for this food challenge. I think it's really interesting to learn from in retrospect. And if you want to get engaged a little bit more on some actual research itself before you're moving to the funding stage, NASA's Gene Lab analysis working groups are a really fantastic opportunity for that. So they're all about democratizing the omics data that comes from spaceflight and ground studies that are often difficult to directly get funding to obtain yourself. And so they have these volunteer-based working groups where folks are able to look through all this omics data and conduct analyses. And similarly, they have an artificial intelligence for life in space working group that's primarily focused on building machine learning models to predict different physiological effects of spaceflight environments. And we see we've got 3 minutes. So as far as funding goes, now into sort of the third tier of opportunities and resources, we will, in our FFS programs, have a workshop that will cover more in depth how to navigate NSPIRES, which is where NASA lists all of its solicitations for grant funding. But I did want to bring to your attention just 2 recurring grant opportunities. The first is this HRP Omnibus. So it's really, why I think this is interesting is it's a short and a little bit smaller, but it's a great way to get engaged. So it's for investigation into any of the risks or gaps in the human research roadmap. And so it did just close for this year, but please keep it on your grant radar for future offerings. And similarly, if you're coming here as an industry researcher, we want you to be aware of the SBIR and STTR programs that NASA has. Trish also has great offerings. I want to just highlight very quickly, it's coming up very soon, the 2025 postdoctoral fellowship. It's a really exciting opportunity, and it's a great way for postdocs to get a nice little bump in their stipend here. So if it's already on your radar, that's fantastic. If not, it's a little late, but just more motivation to stay tuned for these kind of opportunities as they come up in the future. And lastly, I wanted to mention the Space H, sort of a space health accelerator. So with NASA, Trish, and Starburst, the idea is it's a 13-week accelerator program, and the inaugural cohort application just closed in June, but this is expected to be an annual program offering. So again, for any industry-aligned folks here, it's a great way to get involved and have your venture be sort of shaped towards the real priorities that you'd be able to meet for space. So with that, we are all through our slides right now, and we have 1 minute to go. So we will send you notification when the recording of the webinar is complete. We will also have follow-up answers from Mike to any of the outstanding questions here. Thank you so much for your time. With that, until next time, cheers.